So this lecture is about the linear regression model when we have time series data. Specifically, we're going to do the static model in this lecture, leaving the dynamic model for another lecture. So the setup for this lecture is that I have time series data on a bunch of variables. One of the variable is the dependent variable, and I have k-1 explanatory variables. So the data could be monthly, weekly, or yearly. That makes no real difference. But each time series is observed over the same time period. It's time series data, so I'm not going to assume that we have a random sample. Instead, we'll assume that each time series is a stationary process. So the dependent variable is a stationary process, as well as the time series for each explanatory variable. We use the stationarity in the weak sense, so that means that the expected value for each time series is constant, the variance is constant, and the covariance between two observations in time depends only on the distance in time, how far apart they are. So when we have this kind of data, we can formulate a linear regression model, and the linear regression model looks pretty much the same as it does when we have cross-sectional data, with the exception that we use the t subscript instead of the I subscript. So the dependent variable at time t depends on these k-1 explanatory variables and their values at time t as well. Plus, we have this additive error term. With cross-sectional data, it's generally acceptable to make the random sample assumption. So when we make the random sample assumption and we have cross-sectional data, then one of the key assumptions, additional assumption in the linear regression model, was the exogeneity assumption. Now with time series data, when we have kicked out the random sample assumption, the exogeneity assumption will still be important, but it will look slightly different. So let's move on and investigate the exogeneity assumption in time series models. So just a quick review in the case where we had a random sample and cross-sectional data, we could write yi is beta 1 plus beta 2 xi plus epsilon I. We could make the assumption that yi and xi is a random sample. And by that we mean that we have independence across observations. With the random sample, we specify the exogeneity assumption as the expected value of the error term conditionally on xi must be equal to 0 for all I and all possible values that xi can take. So in terms of, for example, I equal to 1, it says that the expected value of the first error term given the x value of the first observation must be 0, and so on. Now, would it make sense to claim that the expected value of the first error term conditionally on x1 and x2 should be equal to 0? In this case, this is the x value for the first observation, and that's the x value of the second observation. Well, the answer is we have made the assumption of a random sample, so anything with a subscript 2 will be independent of anything with a subscript 1. So we know for a fact that these will be independent, and it really makes no sense conditioning on x2 because we know that that will not provide me any information about the observation with index 1, so we can cancel that, it makes no difference. Well, moving on to time series data, yt is beta 1 plus beta 2 xt plus epsilon t. This combination of yt and xt is no longer a random sample. This is not a random sample. That means that suddenly it is possible that a random variable with one subscript is correlated and dependent on a variable with another subscript. So in this case, expected value of epsilon 1 conditionally on x1 and x2 is not necessarily the same as the expected value of x1 conditionally on x1 only, simply because of the correlation. Since there is a correlation between x2 and x1 perhaps, and x2 and epsilon 1 even, then we cannot exclude the possibility that an x variable at another time point will affect the error term at time point t. So because of this, we need to change the exogeneity assumption from this condition in the case of cross-sectional data when we have a random sample to this condition. With time series data, and the exogeneity condition will look like this. Expected value of epsilon t conditionally on x, and by x I mean now this is just shorthand for x1, x2 all the way to xt. So I'm conditioning on the x variable at all time periods. And the requirement is that the expected value of the error term should be 0, no matter what the x variable takes as a value, not just today, but in the previous period, in the next period, and so on. So an important conclusion will follow from this. Remember that one very important case when exogeneity was violated in the case of a random sample was that if the error term was correlated with the x variable for the same observation, if the error term was correlated with the x variable, then exogeneity would fail. Then the expected value of xi given expected value of epsilon I given xi cannot be 0, because then the expected value of epsilon I will depend on xi. There is never an issue in a random sample case of the error term for individual I to be correlated with the x value for another individual. That's never an issue because of the random sample. But in the time series model, that is an issue. Now it is suddenly possible for the error term at time t to be correlated with the x value at another time period. And we need to rule that out if we want the exogeneity assumption. So if it's the case that epsilon t is correlated with the x value at another time period, at xs, perhaps previous time period or next time period, then exogeneity fails. A necessary condition is that the error term is uncorrelated with all the x variables at every point in time. And just like in the case of cross-sectional data, a sufficient condition would be that the error term was independent of the x variables at all point in time. If the expected value of the error term was also equal to 0, then it would also be okay. So let's summarize this. The x variables are exogenous if the expected value of the error term at time t given all the x variables at all points in time is 0. And this conditioning on x is just shorthand notation for conditioning on all x variables at all points in time. So if it's the case that the explanatory variables are exogenous, then just by taking the expected value of both sides of the regression model, we see that the expected value of yt conditionally on all the x's is this linear function of the data. So by conditioning on every x variable at every point in time, if the expected value of yt is then just a linear function of the x variables, then the x variables are exogenous. That means that with the exogeneity assumption, we can write the regression model in this compact form, just like we did for the case when we had cross-sectional data. Again, there's just one tiny difference, and that is we don't condition on xt, we condition on x. If I move the conditional expectation to the right-hand side, we actually have the definition of the error term in a linear regression model. So this is how we define the error term, simply as the deviation, the difference between what we observe for y and what we would expect to observe for y given the x data. So with this setup, we can actually explain now the difference between the static model and the dynamic model. Again, just to remind you, the key point here is that I'm conditioning on all the x data, not just xt. So we say that the model is static if only observations made at time t affects the expected value of yt conditionally on x. Note, I am conditionally on all x data at all points in time. So it is allowed for this expected value to depend on past values of x as well. But if it turns out that this expected value does not depend on past values, then we say that the model is static. If you think about this from a more sort of economic perspective, it basically says that the explanatory variables, the value that they have in this period, whether it's monthly data or yearly data, that's what's important for determining the y variable in the same period. It's also possible that past values affects the conditional expectation. And if that's the case, then we say that the model is dynamic. We'll look at this much more closely later on when we look at the dynamic models. But it's certainly possible that the effect of an x variable at the previous point in time lingers and affects a y variable at a later point in time. And if that's the case, the model is dynamic. Alright, so we talked about the exogeneity assumption in terms of time series models, and it's just a slight modification here. Just change the conditioning from xt to all of x. Actually, going further with the homoscedasticity assumption in time series models, the change is very much similar. Remember, in cross-sectional data, we said that the error term was homoscedastic if the variance of the error term for observation I conditionally on xi was constant, but we did condition on xi. Well, guess what? For time series models, we say that the error terms are homoscedastic if the variance term of epsilon t conditionally on, and now not xt, but all of x, is constant. So given all the x data at all points in time, if the variance of the error term is constant for every point in time, then we say that the data is homoscedastic. We needed the homoscedasticity assumption in order to claim that the standard errors were consistent in the OLS models. If we didn't have homoscedasticity, then we lost that and we had to either change the method to weighted least squares or we had to do robust standard errors. And we also found out that if the errors were heteroscedastic, then OLS were no longer efficient. Well, we'll see that something very, very similar will happen with time series data. So if this conditional variance depends on any of the x variables, and it's actually okay even if it depends on the x variables in the previous period, even then we say that the error terms are heteroscedastic. Now, in cross-sectional data with the random sample assumption, we only had these two assumptions in the Gauss-Markov theorem. We required exogeneity and homoscedasticity. For time series data that's stationary, these are important assumptions for the Gauss-Markov theorem, homoscedasticity and exogenous x variables. But unfortunately, there will be one more assumption that we need for the Gauss-Markov theorem, and that's the assumption of no autocorrelation. So let's discuss autocorrelation. So this is not so hard to understand. We say that error terms are autocorrelated if, given all the x data, the covariance between two error terms at two different points in time is not zero. If the covariance is not zero, the correlation is not zero. So the term autocorrelated really means sort of correlated with itself, and that's what's happening here. Epsilon t is correlated with itself at another point in time. Remember, this is between the error terms, so we're not excluding a possible correlation between the x variables at different points in time and between the y variables at different points in time. But the error terms, if I want the data to be not autocorrelated, should not be correlated over time. So if we don't have autocorrelated data, and then we just simply say that we have no autocorrelation, and for that to be true, this covariance must be zero whenever t is different from s. No error term can be correlated with any other error term at a different point in time. So let's summarize the Gauss-Markov assumptions for the linear regression model when we have time series data. First, the replacement for the random sample will be the stationarity assumption. So all data is stationary. The exogeneity assumption, that also exists in the cross-sectional data case, although with a slight modification in the definition. The third assumption is that the error terms must be homoscedastic, and the fourth assumption is that the error terms cannot be autocorrelated. We will look at this issue of autocorrelation more carefully in a couple of lectures later on. So what we will see in the next lecture is that if you have time series data and these Gauss-Markov assumptions are applicable, then you can actually estimate the model using OLS, and everything that you know about the OLS estimates will still hold true. But more on that in the next lecture.